Hey, next up, we have Alex from Matter Labs, who's going to be talking about bringing EVM Smart Contracts to ZK Rollup with zkSync. Please leave your questions in the stage chat, and we're going to do a Q&A after the talk. But take it away, Alex.
Thank you, Anna. Thank you for having me, and hi, everyone. Welcome to the talk about ZK rollups, optimistic rollups, and EVM smart contracts and how this all can work together. And we will start with the intros into rollups. I'm sure that most of the audience is familiar with it and know what rollups are and the differences between optimistic and ZK rollup in principle. Very high level, so I'm not going to repeat it because there's been a lot of content on this topic over the past 2 years. If you're interested, I can send links after the session to deep dives and comparisons. But rollups are on the rise. Ethereum is now officially a rollup-centric platform. The Vitalik Buterin recently announced the adjustments in ETH2 roadmap and ETH1 roadmap to focus on the rollups and make sure that they are first-class citizens. And essentially, it's now kind of official that rollup is scaling. Ethereum is scaling with rollups. Everything else has way inferior security and decentralization properties, so rollups are the kings. Interestingly, there are 2 flavors of rollups, and we're going to compare them. They share the common basis. In both types, you have one contract on the mainnet, which holds all the assets and a single cryptographic fingerprint of a state, for example, a root hash of a Merkle tree. And for every new block which happens off-chain, which contains a lot of transactions, only this one hash is changed on the mainnet contract. Now, for ZK rollups, you have to, as an operator, so whoever submits this block, they have to provide a zero-knowledge proof of validity of that block, testifying that the new hash was correctly derived from the previous one. In optimistic rollups, no modern cryptography is used, and instead you rely on game theory. And someone has to monitor all the transactions in the rollup and has to submit a fraud proof to Ethereum within a predefined period of time to challenge the fraudulent transactions. And in order to be able to do so, and for both types of rollups, in order to be able to reconstruct the state and be able to prove that you still have some ownership, the data for every transaction is posted through Ethereum as call data. So for each transaction, we post either the input, which everybody can take and re-execute by applying it to their previously known state, or maybe just the delta of the state, what changed in the state, like which slots get what new value. And yeah, so these are the technical differences, which as I said, you can check extra. Let's focus on the properties, like what is different between the 2 types of rollups. And just to mention, ZK rollups are currently in production. So we are, for example, authors of zkSync, which can be used for payments, and not only for payments, for transfers of value of any kind with ERC20 fungible tokens, for example, for airdrops, for different like payments as a checkout in applications. For example, we used it with Gitcoin grants of the last round. I'm going to use it with round 7 in December. We natively support multisig, so you can implement some multisig based applications. With multisig, you can actually do very interesting things such as atomic swaps, payment links, and like some basic contracts. And you can also send payments to any Ethereum address. So for example, you could send payments to a smart contract, and then this smart contract can request from the mainnet to get the funds back to mainnet from the rollup. So there is a lot of flexibility, but it's not a fully functional smart contract platform. And this is what everybody needs, because we all want to scale Ethereum in general, with DeFi, with all the cool things which smart contracts were invented for. So for that, let's see how this stands. So optimistic versus zk rollup. There are a couple of differences which, in my opinion, clearly benefit zk rollups. And I think it's very, very important to understand these differences in order to see the importance of porting existing contracts to these systems, and specifically to zk rollup. So number one, the most crucial distinguishing factor between the two rollups is the security model. In optimistic rollup, you rely on one-off and honest validators assumption. In zk rollup, you rely on pure math and cryptography. So zk rollup is as safe as the underlying layer one if the cryptography is correct. With optimistic rollup, you're supposed to be safe if at least one of the validators is correct, is not compromised, which per se is a reasonable assumption, but people often ignore that it's not the only assumption of optimistic rollup. There is another one, and it's a lot nastier. You also rely on the mainnet Ethereum to be enough censorship resistant so that any fraud-proof transaction reaches the optimistic rollup contract. And that is actually pretty problematic because there are attack vectors where you can deploy a 51% attack on Ethereum mainnet and censor a specific smart contract for a week, which costs not a lot. Like the brute force cost of this attack is something like $20 million. And if it's successful, you can just grab all the assets from the optimistic rollup. And interestingly, the actual cost of this attack is a lot lower than $20 million because it's enough for you as an attacker to just make a plausible commitment to the threat to override other blocks from other miners who are not compliant with you. And so you run the attack for a short period of time, and you communicate to everyone that, hey guys, you should be censoring this contract. If you don't do this, I'm going to override your blocks, and you're going to lose money. And rational miners, being anonymous and being able to shift hash power flexibly from one mining pool to another, they don't have anything to lose if they comply with you, but they have a lot to lose if they don't comply. So what's likely to happen is that a large fraction of the power will move towards the mining pools controlled by the attacker, and then the cost of the attack will be negligible. It will be just like, I don't know, in the range of 1-2 million. So if you put a lot of value in a single instance of an optimistic rollup, it's an invitation for this attack to happen. So it's probably like not secure to put more than a certain amount. Let's say $50 million is an absolute maximum of what I would kind of think is like not likely to happen in this attack. If you put more money, if you put 100 million, 200, 500, $1 billion, it's almost a guarantee that this will happen. And unfortunately, this type of attack cannot be mitigated as long as Ethereum remains a proof of work chain. So once Ethereum moves to proof of stake and everybody migrates, then you could have some mitigation strategies. Then it would be possible for the community, for example, to have an agreement upfront saying that if this type of censorship happens, then we will consider it a legitimate situation. It's not just code is low, we have some values beyond that, and we can see which miners were or which stakers or validators were participating in this attack. We can target them and slash them. But this is only once Ethereum is proof of stake. So this is probably several years away. And we need to scale Ethereum today because everybody is, of course, familiar with the gas prices rising astronomically this summer. So this is one big, huge problem. The second biggest problem is that optimistic rollups have a very long objective finality. So time for layer one to understand that a certain block is final on an optimistic rollup, so that you can process exits from the optimistic rollup, is equal to the fraud-proof delay. So like, this is a security parameter which is equal to 1 or 2 weeks. Let's say it's 1 week. So any native withdrawal from an optimistic rollup will take 1 week. All the NFTs will take 1 week. Fungible tokens could be accelerated if you use some external liquidity which is available on the mainnet. So you can ask somebody who is on mainnet to give you immediate liquidity and then wait for this 1 week to withdraw it from the rollup, and you're going to pay for it. So of course it's going to be expensive and it's going to be complicated in terms of coordination. Maybe this will work with some smaller amounts of fungible tokens or of liquid tokens, sorry, but like for some less liquid tokens and for very large amounts, if we're talking about moving half of some DeFi protocol on a layer 2 and back to layer 1, this might be really problematic. All of this, of course, you don't have with zk rollups, because in zk rollups, the time of exit is equal to the time of finality, which is just a couple of minutes, which are necessary to construct the zero-knowledge proof. And finally, you have certain types of transactions, most specifically transactions involving privacy, which are going to be a lot more expensive on optimistic rollups than on zk rollups. So for example, for privacy, you have to publish all the zero-knowledge proofs, which can be pretty large. So a Plonk proof, for example, is 1 kilobyte on the optimistic rollup, and you can completely omit them in the zk rollup, which supports recursive zero-knowledge proof verification. So the cost of a private transaction in zk rollup will be something like 2 times normal transaction. For an optimistic rollup, it's more in the range of like 20, 50, 100x. So it would be, from this comparison, we can see that it would be absolutely awesome if we could just put existing contracts on zk rollup, and many people have considered it a very difficult task. That's why we had a lot of attention to optimistic rollups over the past year. But this is actually not true anymore. It is possible to port existing contracts to zk rollup, and let's see how we can do this. So let's go through a migration roadmap, which we in the Meta Labs are following and planning to process to get all the legacy contracts on the on zkSync specifically. We start with just supporting contracts which are zero-knowledge proof friendly, and to be zero-knowledge proof friendly, the most obvious approach is to have a non-Turing complete contract support, which we did this year with Zinc. What is Zinc? It's a language for constructing smart contracts and also doing generic computation, like producing zero-knowledge proofs, based on Rust. So this is an example of the code of Zinc. It follows the Rust syntax. It borrows the smart contracts elements from Solidity, but apart from that, everything is like pure Rust, except for we eliminated all the complex elements which people normally hate in Rust. And Zinc comes with some nice features. So it's completely type safe. You can define custom types. You don't have to bother with all this mess in Solidity where you use the same uint8 for a number and for some option and for some amount. You can define types for every single thing separately and make sure that you don't mix them up. It has type inference, which makes the syntax a lot nicer. So we have some syntactic sugar built in the language. It's immutable by default, and it supports safe math, which the newest version of Solidity also supports, but we were there a year ahead of Solidity. So natively with operators, all operators are safe. You cannot have an overflow in the operations of simple math. Immutability is really important. So Rust is a functional language, and it allows you to have a lot less side effects and make the code a lot cleaner and a lot less buggy. And for smart contracts, this is very, very important. So you can check it out at zkSync.io. A nice thing is that Zinc comes with a packet manager called Zargo, on the analogy to cargo in Rust, which gives you lots of options. So you can go and have you can create projects, you can build them, you can manage your files in with like you can have a project consisting of multiple modules broken down in several files. You can run tests, you can do benchmarks, and so on and so on. So like lots of useful functionality, all from command line, following a nice command line syntax. You will also be able to generate documentation and format the source code. So, but testing is really, really important. You can write your tests also directly in Zinc and have a really nice unit testing experience, a lot nicer than in Solidity. Essentially, I'm of course biased, but like every single aspect of the language is better than Solidity, in my opinion. I would encourage you to check it out and experiment yourself. So we have Zinc, and you can do contracts. Zinc is non-Turing complete, so it doesn't contain unbounded loops and recursion. You like recursion in a single function call. You can have recursion by calling the contract itself, but it's going to cost you like an external call. A really nice property of Zinc is that you can do. We paid a lot of attention to debugging, and you have, for example, console log traces, which can be run on transactions which are running on testnet or mainnet. So you can have a smart contract call which does something and fails. And in Solidity, it's totally difficult to understand what happened. In Zinc, you can just add more debug points with console traces and just rerun. So you can modify the code and rerun the same transaction on the exact same block in the exact same spot with extended logs and actually see what's going to happen and why the transaction is failing. It's really like a lot simpler to debug with this kind of approach. So okay, we have that, and it actually works. So you can take existing smart contracts and just manually rewrite them into Zinc today. And this is what we did with Curve. The original Curve is written in Vyper, which is also a non-Turing complete language. It doesn't allow unbounded loops and recursion. So what we did, we just took the code and rewrote it line by line into Zinc. So the code is public. You can go to Exchange and see how it looks. It's almost exactly like line-to-line translation of the original contracts. And if you go to the Curve homepage, you will see. Oh, sorry, you probably don't see my screen. I want to show this one. Okay, so let me just go back here. Here is the contract code, and under MetaLabs /Curve Zinc in GitHub, this is how it looks. This is how the tests look like, the code itself. And if you go to the Curve homepage, you will find a link to the zkSync testnet right there, which is also hosted by Curve. And you can just try it out. So you can go and connect your wallet, which will open a separate tab, so you won't see it now if I do it, but you're welcome to experiment. You will get some test stable coins on the Rinkeby testnet to play with, and you can just do a swap and see how this works with any wallet which supports Web3. So with MetaMask, Wallet Connect, or even with a burner wallet, which will live inside your browser. So this works. You can do this now. Okay, so this was the second step. Now the third step is we can automatically convert legacy code into Zinc, even if it's written in Solidity, since Zinc and Solidity are structurally isomorphic. Except for the Turing complete part, every aspect of the language is like, though they're following different syntax styles, they are the same. So you just define your contract, you define your state, you define your public-private methods, and we actually implement this. Okay, let me just share my full screen. I think I can do this. Okay, we have an experimental transpiler from Solidity into Zinc, just called solz, and yes, this is how it works. So I just transpiled the Uniswap code and produced a uniswap.zn, and here is how this code looks like. It's almost complete in terms of, so it compiles. Some lines of code are still commented out because they are unsupported, but we are almost there with the full support of Solidity to Zinc transpiler, and it will be possible to compile anything except for the Turing complete parts, which you will have to rewrite. The good thing is most DeFi contracts do not require Turing completeness. So Uniswap is non-Turing complete. Most other things, even if they have some loops, mostly what you need is just to iterate through a couple of things. So they are not, most of DeFi protocols, like if you look at the top 10 from the capitalization standpoint, they only iterate through some fixed number of items and maybe number of pairs in a trading loop for curve or something like that. So like most of the time you can just easily convert it with minimal modifications and it will just work. Okay, and finally, so yeah, this is how the Uniswap code looks here again. And finally, we are currently working on adding Turing completeness. Once we can add Turing completeness, the transpiler will, of course, easily support transpilation of any code, and it will not be required to do manual changes at all. It will just work. So it will be possible to just take any existing Solidity code and deploy it to zkSync without need of modifications. And what made this possible were two things. Number one is recursion, which we implemented for Ethereum with Plonk in summer for the Reddit challenge. So if you go to reddit.zkScan.io, you will see the block explorer with the recursive blocks, and they're coming to mainnet actually next month. So this is fully functional with Ethereum verifier on Rigipi testnet, and this allows you not only to have arbitrarily many blocks verified with a single proof, but also to have separate runs for every contract verified in one big block. So a block can contain multiple transactions, and each transaction will have its own smart contract call with a separate proof, and you can aggregate all of them together. So this is one approach. Another approach would be to build one generic circuit, which I think Cairo is following, but we think that what we're doing with recursion is a lot more flexible because it gives us ability to have contracts which are using some very advanced crypto, like using some non-ZK friendly crypto, like SHA-256 hashes or Keccak hashes or Ethereum signatures. And we still are able to efficiently verify them because they will run in this separate circuits written in Zinc. And so this is one breakthrough which made it possible. And the second thing is Turing completeness is very expensive. It adds a lot of overhead on top of the lots of overhead that zero knowledge proofs in general are adding. So we need a lot faster prover, and we are achieving this with FPGAs. So we have an FPGA solution which are now being adjusted for BN256 and is Zinc and AWS F1 compatible, and we're going to bring it live probably by the end of this year with the a lot faster proofs accelerated by FPGAs. So the cost is actually not reduced by a large factor compared to CPUs, but the speed, so latency of the acceleration, and accordingly the ability to produce proofs for a large number of contracts and support high throughput is increased massively. And we're going to publish the benchmarks soon. But this is the final element which gives us this ability to build Turing complete contracts. And that's it from my side. We reserved a large fraction of the stock for questions because we suppose there are going to be a lot of questions. So Anna, I'm giving it over to you.
Great. Thanks for inviting me back. So there's a number of questions. I had a question as well, but let's start from the top where Kev asked, is this an alternative to Solidity or an alternative to something like Circom?
So Zinc is, of course, an alternative to something like Circom or Socrates, where you can just write your code, your circuits, and produce circuits, produce proofs and verify proofs for the circuits. It's written in Rust, so you can embed it into any application. So if you want to use it for zero-knowledge proof generation for circuit building, you can do that. It doesn't require any specific zero-knowledge proof skills. So any programmer who's capable of writing Solidity code or Rust code or Python code will be able to write Zinc code. So you don't have to understand math behind that. You don't have to understand like fields, overflow. Like you're not going to make any mistake. If the code is readable, you can be sure that all the constraints are there. It's completely deterministic. We on purpose, we did not allow any non-determinism. You cannot have external witness. We have a rich library of gadgets which you can use, which are efficient, for example, sorting and other things, and crypto primitives, signature verifications. But yeah, you can use it for that. But if you want to use it for contracts, we have a separate flavor of the language which is just supporting smart contract features, and then you just describe smart contracts in a normal way, and we do all the work behind in the back.
I actually want to ask my question as a follow-up here, because in the Curve example that you shared, I was curious if Curve itself is running on a ZK rollup on testnet, or if it's like the code was rewritten in Zinc, because it wasn't completely clear as to like
the code was rewritten in Zinc, and then we run it on our testnet.
And it would be on as once it's in production, once it's out there, it would be on a ZK rollup.
Yes. So if you, like with any layer 2 solution, you will have to deploy a new instance inside this layer 2, and you will have to move your funds from layer 1 into this layer 2 through some asynchronous process. So it won't be smooth. You cannot just like put existing code on layer 2 and make it interact the same way with layer 1's smart contracts as you did before. What you can do though is you can gradually migrate from layer 1 to layer 2. So Curve, Balancer, and other protocols could just deploy another instance in the layer 2 in zkSync with just a small amount of liquidity, and then gradually, with the increased demand in layer 2, they can move funds from layer 1 to layer 2, gradually like shifting the balance towards more allocation in layer 2, but always having an option to go back should there be something like if you need this money back on the mainnet because there is some hot project going live and you want to participate there and like, do your liquidity mining, you can always do this. Right, so you have full optionality. You don't have the fear that you won't be able to move them back for 1 week, like it's going to be the case with optimistic rollups.
Wei Jay asked, which proof system does Zinc target?
We have backend in Plonk, which will automatically work with Redshift once Redshift is complete. Redshift is our proof system, which is based on the Plonk arithmetization, but uses Fry for polynomial commitments instead of Kate commitments. So it means the Redshift is transparent. It doesn't require trusted setup. Plonk requires the universal trusted setup, which we reuse from the ignition ceremony from last year. So yeah, it's like Plonk arithmetization. So anything which is based on Plonk arithmetization is you will be able to extend Zinc to produce proofs for that system. So yeah, why is that important? Because we're going to use some specific things from Plonk, like some custom gates and lookup tables, which are making certain things very efficient.
Wasob asked, I wonder how Zinc handles 256-bit numbers and the arithmetic.
Like long arithmetics. So you have, just like no processor has 256 bits native words, you have 64-bit words, and then you have like some number of limbs in your number, which is being multiplied like with long arithmetics. The same thing happens here. We can natively support 64-bit numbers because they are not going to overflow even if you multiply two numbers in the field. Yeah, then we have 4 limbs in the representation of a single U256.
Isaac was asking, how are non-snark friendly things like, I don't know how to pronounce this, Kikak or whatever, Kachak, handled
with custom gates?
It's handled in the transpiler.
Custom gates in Plonk. We managed to bring down the SHA-256 constraints from 25,000 in 25,000 R1CS constraints down to 5,000 gates in Plonk. Just one example. So you can do a lot of nice things there with like Plonk allows you to construct something like Starks for certain elements and use them as like the single custom gate.
Star had a question about recursive zkSnarks, but I'm not sure I understand this. Is recursive zkSnark used to support smart contracts? And I don't know if you understand that.
Well, yeah, this is what I said. Like we support, so we aggregate multiple proofs recursively into one, and we can have it in a tree-like structure. We can have arbitrarily many proofs being aggregated into a single one, and each of them can represent a smart contract call, for example. And without that, it would be really difficult. Then you have to construct one single huge circuit which does everything, which might work with Starks, but will have other problems. So I think with Starks, you won't be able to as flexibly have the Ethereum constructs like Kachak and SHA-256. But you, at least on the other hand, you can have one single block which contains like lots of transactions. With Plonk, it won't work because we have a trusted setup of a fixed size, so we can only fit as many constraints in one single proof. But having recursion allows us to combine these proofs arbitrarily many times. So we can have like as many contract calls or execution trace as we need. Sergey
asked, does it support Ethereum precompiles like BN?
It doesn't. No, we excluded. So Ethereum precompiles like SHA-256, yes. So the basic ones, not the BN or like this modern crypto like EAP 1962. No, we don't support that. So contracts that rely on this will have to be rewritten using the crypto primitives from Zinc directly. This is one exception, yes.
Lasso was asking, is the recursion unbounded?
Recursion on the level of calling the contract itself is unbounded. So you can just schedule many calls of the contract. In Solidity, you can do message what's it called? Message sender dot callback, right? But you cannot have it inside the function of Zinc. So it's slightly more expensive, but yeah, you can have it in unbounded way. You can structure it this way.
Cool. Hang was asking, Are the common ZK-friendly crypto primitives already built into Zinc?
We do have a number of common crypto primitives such as hashes, signature verifications. We support MuSig, which is a very popular signature scheme based on Schnorr signatures, which allows multi-sig and just generally is nice to work with. Yeah, hashes that Merkle trees. I don't have it out of the top of my head, but we have a really nice documentation. So if you go to zkSync.io, you will find a complete Zinc book with like the standard library and all the contracts, non-contracts, circuit operations, everything is explained.
I just tried to put it at the bottom there. I hope I got it right.
I'll send this link to the stage.
To the chat.
Chat, right?
Yeah, that'd be awesome. Yeah.
Yeah, this is
great. So Kev asked, does this use R1CS flavored versions of Plonk, or is it standard Plonk with custom gates?
It's standard Plonk with custom gates and lookup tables.
And soon Redshift.
Redshift is work in progress. It would work now. We tested a recursion as well. It supports recursion the same way a Plonk, like Kate-based Plonk supports recursion, but it's just not as efficient with regard to hashes. So once we can bring down the cost for hashes for recursion, it will work. If you don't need hashes, if you don't need recursion, you could use Redshift today. If you have applications which require transparent proof system, you can write proofs in Zinc, compile them into our intermediate representation, and then it will be possible to have Redshift. I'm not sure how like code is already public or not for Redshift, but it's certainly possible. Like you can talk to us if you need that. Just talk to us and we'll figure out.
Dara was asking, did Redshift always use Plonk arithmetization, or is that new? But then following up, it did use Plonk already.
Yeah, we used to use pure R1CS based on Bellman, and we used to use Bellman gadgets, and now we created a bunch of our own gadgets because we needed to bring the costs down. So now we're switching to the Plonk-based arithmetization.
Okay. Isaac asked, do you have custom gates for all non-snark friendly ETH opcodes?
So can you repeat the question?
Oh, sorry. Isaac asked, do you have custom gates for all non-snark friendly ETH opcodes?
No, it doesn't work this way. It's slightly more complicated than that. We don't do EVM. So this is the thing I missed probably in my talk. When we talk about bringing EVM smart contracts to zk rollup, it does not literally mean bringing EVM to zk rollup.
Oh.
This is not what people need. What people need is to bring the legacy code, which now compiles into EVM, which is written in Solidity or Vyper or partly in assembly or Yule. Take this code and make it work in zk rollup. This is the demand, not just like specifically EVM. And we accomplished that by recompiling the codes into Zinc VM. Like recompiling.
I see, there is a new VM.
Yes.
Okay, just not EVM.
Yeah.
Got it. Brendan asked, what's the constraint cost for recursively verifying a Redshift proof in circuit?
I don't remember. It depends on the hashes. So the bulk of computation of recursive verification of Redshift goes towards hashes. So you have to see how many hashes you have. It's comparable to Starks. So you can just look at Starks, see how many hashes you have, and then pick your hash, which has to be like super efficient, very snark friendly. It can be a non-binary tree. It can be a tree of arity 8 or something, because you have some hashes like Poseidon which take more than 2 inputs, and then you just multiply by the number of constraints. So, but I don't have these numbers out of the top of my head. Alex Vlasov would be able to answer this question better. So if you just drop a line to us, we'll reply.
Is Zinc Stack fully open source?
It is open source. We're opening the code once we complete a milestone and we have a stable version. We work on things, we polish things internally before we open them, so that people who whenever we open something, it should be very, very smooth and functional. But yeah, everything will be eventually open source, completely, 100%, including hardware.
Ronald was asking, is there a difference in syntax between the standalone version of Zinc, like the previous 0.15 version, and the new smart contract version of Zinc?
No differences in the syntax of the language itself. We just added features required by smart contracts. So we added keyword contract and the syntax for storage definition for public methods, private methods. But inside the methods, they look exactly the same as normal Zinc, like previous version of Zinc. So Zinc is evolving. We're adding some new features. So obviously, the language just supports them, but they're going both into the smart contracts and into the circuit modes.
Cool. Dara's asking, can Redshift be combined with the accumulation scheme idea?
I'm not familiar with the scheme. Is it the name of the scheme? We've been talking about it
a lot in the zk study club.
Sorry, where?
Maybe it's the third one from the bottom. But Dara, do you want to give a bit of context to the question, maybe? And we can come back to it. I'll ask the next one. Okay. Kev asked, is the 1K proof size for all custom gates plus lookup with KZG?
I
think the question is the combined proof size.
I think it's like 1 kilobyte or 1.5 kilobytes, something like that. So I'm not exactly sure, but it's on the order of magnitude of 1 kilobyte. Yeah, for everything, the complete proof.
Cool. Jekek asked, what's the outlook to disassemble EVM bytecode and recompile for zkSync?
It doesn't make sense because you're gonna lose a lot of important information. For example, if you're using, imagine you have a hash map in Ethereum, right? This hash map has very specific sequence of derivation of the way you address your storage. So you take the slot number, you take the key of your mapping, you make a ketchup hash out of it, and you use this hash as the key for the storage slot, like the index of the storage slot in EVM. So if you just take this natively, this code written in the bytecodes from EVM for this part of code, you will construct a very expensive operation. Whereas if you know that you're dealing with a hash map, you can do things slightly differently and way more efficient. So it's a lot better to work with the original source code because you can derive a lot of information from the source code, from the context there. So it's possible to do EVM transpilation directly, but it's just not going to be as efficient as working with source.
Ronald was asking, is the default access scope of functions the same as in Solidity, public by default?
I can't answer this immediately. I think in Rust, we have explicit modifiers for each function, so you cannot have I think it's the other way around. You have to do pub. Let's see. Let's just look at the code and functions, and I have to go. Yeah. So you have to do pub for a function which is public. So by default, it's private. So as I said, every element of the language is better from the security perspective than Solidity. Every single thing you look into is most likely better, because Rust is now lingua franca of all security. If you look around, Facebook Libra is based on Rust, Alio is based on Rust, Polkadot chose Rust. Lots of new things are being based on Rust because it turned out to be a very good design of a secure language with all the elements which are necessary to prevent common mistakes and yeah, that's why it was a choice for us.
There was a little bit of conversation about Fry and this accumulation schemes, but I think I'm going to let you check that out after. But Dara did have a follow-up, which is more about Redshift here. So what's the concrete efficiency, proof size, prover speed, verifier speed of Redshift relative to Halo?
I'm not able to answer this question. I would refer to Alex V.
Okay. He's the person who designed it or has really been working on it.
He's our chief scientist, yes. So he will, we have multiple people working on this stuff, but he will be able to answer the question. So Dara, I encourage you to just ask him.
Is he here? Is he in the chat, or can we get him to come into gather.town later, maybe?
We can try, yes.
Okay, I think that would be awesome. Martin was asking, apart from implementing, migrating from smart contracts to Zinc, what else would be required to run a solution end-to-end locally or on a testnet? Example of Zinc VM and layer 2 operator code available for local operation. Is the Zinc, is it available?
So for local operation, you just need to run a node. On the testnet, we will support deployment for multiple public testnets, so you don't have to worry about that. And I'm not sure I understand what specifically the question is all about. So you just have to run a node, right? You can do it with Geth locally, and if you want to have it on your own Ethereum testnet, you can just have a local testnet and a local installment of zkSync, and then it will work. Kind of.
Cool. Kev asked, did you also copy Rust demand-driven compilation process?
What is demand-driven compilation process?
And maybe if you can clarify, Kev. Also, I'll say it now. If there are any last questions, we should probably put them in the chat now. I think we have a few more minutes to take some. There's some really good conversation happening here, and I like that. Isaac, and you're answering questions. This is fantastic. I'm wondering if there's a way for me to export this after. I'm gonna have to check it out. But yeah, Kev, if you want to maybe just give a bit of context on that Rust demand-driven compilation process you mentioned. Also, Alex, you know that there's a 30-second delay, so we have to wait for a moment.
Sure.
I had a little in-between question maybe, which is about the Gitcoin project that you did. With that, was there a Zinc VM running? Is that also smart contract enabled, or was that something else?
No, it's very simple. It's just payments.
Okay.
Payments are very stable now. They can be used for with wallets. We're integrating them into smart wallets. They are simple, running for a long time, and have proven themselves robust. Contracts are more experimental.
Okay. Ethereum Working asked, Alex, could you explain more how the permissionless network of zkSync operators working together to ensure the service availability?
Sure. We'll have a consensus in layer 2 with validators requiring, they'll have to put some zkSync tokens at stake to become a validator and produce blocks. And so the way they produce blocks is similar to a normal sidechain, with the only exception that once they produce a block, in order for this block to be actually happening on Ethereum, they also have the block producer who is elected to produce this block will have to generate zero knowledge proof and submit it to Ethereum. But the coordination will happen in this off-chain consensus.
Cool. So Kev came back with some clarification on that earlier question. Is the new architecture that Rust is employing where compilation is no longer multipass when you need to type check an expression, for example, you query for the expression type, and there's a document that is linked there.
I'm not the expert on compilers, so I answer that exactly, but we simplified Rust. We have a, I'm not sure if it's multipass, so it's probably multipass, but we don't do a complex type inference. And the reason for this is that a lot of people are having difficulty with Rust because of unreadable error messages. Like they do something, and then the compiler is so smart that it thinks that it should do some like very complex time inference with templates, and it's probably some difficult construct which it doesn't understand, and it outputs a compiler error which is absolutely incomprehensible. So we wanted to avoid that. We definitely wanted people not to have this experience and be like that. Every error message is very helpful and helps you understand immediately what's going on. So because of that, we had to simplify something. So like the type inference is very simple. It doesn't require like, and that's why we don't have like full templates. Also, you don't need them in the smart contract.
Wei-Jay, going back to the custom gates, just to clarify, does Zinc have custom gates for SHA-256? Is there a full list of operations with such custom gates?
We will publish it with the release of the next version of Zinc, but SHA-256, KCHAC, we do have custom gates for them.
Cool. Well, I'm going to assume that there's no more questions because it's been a moment since we've seen one. If there's any missed, I'm really sorry. We're going to head to gather.town just after this. So maybe, Alex, if I can get you over there too, we can continue the conversation there.
Sure.
So thanks again.
Thank you guys for listening. See you soon.